Welcome to the Deep Dive. Today, we're plunging into some really mind-bending cosmic news that just landed. I mean, stuff from the farthest reaches of the universe, but also spectacular shows happening right in our own night sky. There's just an incredible amount of stuff coming out, it feels like, every single day. So our mission today is to take this fascinating stack of recent articles and, unpack some of the cutting-edge insights. We're going to explore how stars are born and sometimes, apparently, reborn pretty dramatically. Also, how humanity is pushing the boundaries of space exploration with a bit of help from AI. And maybe, best of all, what incredible celestial events you can actually see for yourself tonight. So get ready for some serious aha moments. Hopefully you'll leave feeling well-informed and maybe even inspired to just, look up. Okay, let's unpack this first one. This incredible story from the Hubble Space Telescope. They've revealed something pretty astonishing about what looked like a totally ordinary white dwarf star, WD 0525 plus 526. About 128 light years away. Now, apparently it looked completely normal in visible light. So how did Hubble even start to figure out it had this turbulent origin story? Was it hiding something?
It absolutely was. You see, a white dwarf is typically the dense remnant left over when a star like our sun runs out of fuel and collapses. It's the path our own sun is likely to take in, about 5 billion years or so. We usually think of them as pretty quiet, predictable endpoints. The result of a single star just evolving on its own. But this one, well, it had a secret past.
A violent secret past. So it wasn't just one star evolving. It's the result of two stars actually colliding and merging.
Precisely. A really violent event. And the clues, they were only visible in ultraviolet light. Hubble's UV instruments, they pick up an unusual amount of carbon in its atmosphere.
Carbon? But shouldn't that be hidden?
Normally, yes.
Huh.
White dwarfs usually have these outer layers of hydrogen and helium, kind of like a shell, that hide the carbon core deep inside. But in these really intense high-energy mergers, those outer layers can get completely stripped away.
Oh,
yeah. Allowing the carbon from the core to sort of float up to the surface where Hubble's UV sensors can spot it. It's like peeling an onion, really.
Yeah. Wow. And this isn't just any merger remnant, right? It's extreme even compared to others they've found.
It is. WD 05205 plus 526 stands out. It's hotter, nearly 21,000 Kelvin. That's about 37,000 degrees Fahrenheit.
Whew.
And it's more massive, too, about 1.2 times the mass of our sun. That puts it at the top end, even for this rare category of merger remnants.
So does that push the boundaries then? Does it make astronomers rethink what's possible in these collisions?
It certainly does. And here's the really interesting bit. Since this star looked totally normal in visible light, astronomers are now wondering how many other white dwarfs out there might be hiding similar explosive origins.
Right, like cosmic sleepers.
Exactly. If these hidden mergers are more common than we thought, we might need to rethink how we catalog and classify white dwarfs altogether. It challenges our understanding of how often these violent stellar deaths happen, and also maybe how common white dwarf binary systems are.
Then those are important for things like supernovae, aren't they?
They are. Understanding these binaries is crucial for predicting certain types of supernova explosions. So, yeah, big implications.
Okay, so speaking of dramatic origins, let's switch gears from dying stars to the universe's birth. There's this groundbreaking experiment recreating the universe's first molecules. That sounds fundamental.
It really is. You have to picture the universe just after the Big Bang, maybe 13.8 billion years ago, incredibly hot. But as it expanded, it cooled down enough for the very first elements, hydrogen and helium, to form. Then, hundreds of thousands of years later, these atoms started to combine, and that's when the first molecules appeared.
And the very first one, the star of that origin story, was the helium hydride ion, He+, correction. Why that specific one? What made it so critical? Like, what if it hadn't formed first?
Well, He+ played this crucial role in early star formation. Think of it as a cosmic facilitator.
Right.
In that young, cooling universe, it helped other atoms and molecules collide more easily and, importantly, release heat. That heat release was absolutely essential. It allowed nuclear fusion to actually kickstart inside protostars, those baby stars, even when things were still relatively cool overall. Without He's plus, getting that first fusion going would have been much harder, much less efficient. It could have seriously delayed the appearance of the first stars.
Maybe by millions of years.
Potentially, yeah. It would have changed the whole timeline.
So how on earth did they recreate this in a lab?
You mentioned storing ions at incredibly cold temperatures. Minus 449 Fahrenheit.
Minus 267 Celsius, yeah. Just fractions of a degree above absolute zero. They held these ions for up to 60 seconds.
Wow. Just holding them there sounds tricky.
It is. And then they forced them to collide with heavy hydrogen, deuterium, to see how they reacted under those early universe conditions. And the surprising finding, the real kicker, was that the reaction rates between these particles don't actually slow down significantly at those incredibly low temperatures.
They don't slow down. But didn't everyone assume they would? Pretty much. Older theories and assumptions were that as the universe cooled, these chemical reactions would become much, much slower, less efficient. This experiment directly contradicts that.
So this isn't just tweaking a number, it's like rewriting a whole chapter in the universe's baby book, isn't it?
You could say that. If these reactions were happening faster, more efficiently than we thought, it implies the early universe might have been ready to cook up stars much sooner.
Which changes our models for how quickly cosmic structures formed.
Exactly. The biggest ripple effect is that it calls for a complete reassessment of helium chemistry in the early universe. These He-H plus reactions seem to have been far more important than we previously assumed. Our models for how molecular clouds collapsed, how fast the first stars ignited, they might need significant revision.
Fascinating. Okay, so from billions of years ago, let's jump way forward to our future in space. NASA's Artemis program, aiming for the moon and eventually Mars. They face some pretty big challenges for long trips, right?
Well, absolutely. And one of the biggest hurdles for long-duration missions, especially to Mars, is the communication delay. Light itself takes time to travel. For Mars, depending on orbits, it can be up to like 45 minutes for a round-trip signal.
45 minutes, just for question and answer.
Yep. So imagine a medical emergency. You can't have a real-time consultation with a doctor back on Earth. It's just impossible.
And you can't exactly turn around and come home quickly either.
Not an option.
So what's the solution? I read about NASA working with Google on something.
That's right. They're collaborating on the Crew Medical Officer Digital Assistant, or CMOD.
CMODA.
Oh, essentially, it's an AI-powered medical assistant for astronauts.
An AI doctor in space. How reliable can that be, though? Especially in zero-G, high-stress situations. Are they testing that rigorously?
That's the key question, and yes, they are. The AI is trained on a massive amount of spaceflight medical literature, using natural language processing and machine learning. The goal is for it to provide real-time analysis, understand symptoms described by the crew, and help them autonomously diagnose and even treat issues.
Autonomously?
Wow. Yeah. Early results from simulations are apparently promising in terms of reliable diagnoses. But you're right, the real test is going to be how it performs in actual spaceflight conditions under pressure. They're running tons of simulations, different medical scenarios to build that confidence.
Still, the potential is huge. And what about back here on Earth? Does this kind of tech have applications down here?
Oh, absolutely. Think about remote areas, rural communities, disaster zones, maybe even workers on oil rigs or cargo ships far out at sea.
Places without easy access to doctors.
Exactly. Having an AI assistant that can process complex medical info and guide someone, even a non-professional, through diagnosis and basic treatment, that could be revolutionary. It's a really great example of how pushing the boundaries for space exploration ends up having direct benefits for us here on Earth.
Okay, so we've gone from ancient stars to AI doctors, but you don't always need fancy tech to experience the cosmos. Sometimes the best show is right above us. And apparently, tonight, August 18th into the 19th, there's a chance to see the northern lights, even further south than usual.
That's the forecast, yeah. What's happening is there's a large coronal hole in the sun. Think of it like a gap in the sun's outer atmosphere. And it's spraying out a fast-moving stream of solar wind particles towards Earth.
Okay.
When this stream hits Earth's magnetic field, it kind of buffets it, causing a disturbance.
Yeah.
We call that a geomagnetic storm. In this case, it's expected to be a minor, or G1 storm.
Yeah.
But that's often enough to spark visible auroras.
So NOAA is predicting the KP index. That's the measure of this activity, right? We'll hit KP5. Is that good?
KP5 is considered a moderate storm level. So yeah, it significantly increases the chances of seeing aurora, especially if you're in the right place.
And the prime time. When should people be looking?
The peak activity is expected roughly between 11 p.m. and 5 a.m. Eastern Daylight Time.
Okay, so late night, early morning on the East Coast.
Right, that corresponds to NU 300 to 0900 UTC on August 19th.
And where might people see this? You mentioned further south.
Yeah, the forecast suggests potential visibility in up to 15 U.S. states, obviously Alaska, but stretching down through parts of the northern tier states, maybe even as far south as Iowa, possibly northern Illinois or Indiana if conditions are perfect. It really depends on how strong the storm actually gets and your local sky conditions.
Got it. Any tips for people who want to try and see them?
Definitely. First, get away from city lights. Darkness is key.
Right. Light pollution is the enemy.
Absolutely. Find a spot with a clear view to the north, preferably with a low horizon. Look up mainly between midnight and 2 a.m. local time, but honestly, start checking as soon as it gets properly dark. And be patient. Auroras can flicker, fade, then flare up again. Sometimes they start as just a faint, kind of grayish-green glow.
Almost like a cloud?
Sort of, yeah, until they get brighter. Oh, and maybe check out some space weather apps on your phone. They give real-time forecasts and alerts.
Good tip. Okay, northern lights. What else is up there right now? Mid-August sounds like a good time for sky watching generally.
It really is. Beyond the aurora, there are 3 particularly spectacular star clusters that are well placed for viewing from the northern hemisphere right now. Real cosmic jewels.
Star clusters. So groups of stars all born together.
Exactly. They're gravitationally bound groups that formed from the same giant cloud of gas and dust. There are 2 main types. You've got open clusters, which tend to be younger, looser collections of maybe dozens to hundreds of stars. They hang out in the spiral arms of the Milky Way, like ours. Over time, they tend to drift apart. We know of over 1,000 in our galaxy. Think of them as like young families or neighborhoods.
Okay. And the other type?
Globular clusters. These are the ancient ones. Tightly packed spherical swarms containing hundreds of thousands, sometimes millions, of really old stars. They mostly live out in the galactic halo, this kind of extended sphere surrounding the main disk of the Milky Way, like ancient dense cities orbiting the galaxy. We know of about 150 around the Milky Way.
How easy are these to see? Do you need a massive telescope?
Not necessarily. Some are actually visible to the naked eye, but they might just look like a faint fuzzy patch, a sort of milky smudge. A decent pair of binoculars, say 10 by 50s, will really bring them into focus, resolving some of the individual stars, especially in open clusters. But a telescope, even a modest one like a 6-inch reflector, reveals their truly magnificent nature. Globular clusters especially just explode into thousands of tiny pinpricks of light. It's breathtaking.
Any viewing tips for clusters? Similar to auroras?
Similar in needing dark skies, definitely. Let your eyes adapt to the dark for a good half hour. And try using averted vision.
Averted vision? What's that?
It means instead of staring directly at the faint object, you look slightly off to the side. Your peripheral vision is actually more sensitive to faint light. So looking away slightly can make the cluster pop into view more clearly.
Huh, clever trick. And apps can help find them too, I guess.
Oh yeah, astronomy apps are fantastic. Put your phone at the sky and it'll show you exactly where to look.
So which 3 specific clusters should people look for right now?
Okay, first up, the absolutely stunning Great Hercules cluster, also known as M13. This is a globular cluster about 25,000 light years away, packed with maybe 100,000 stars. It's incredible.
Where do you find it?
Look for the constellation Hercules. There's a distinct pattern of 4 stars called the keystone. It looks like the central stone in an arch. M13 is located along one side of that keystone. Binoculars will show it as a fuzzy ball. A telescope starts resolving those stars.
Okay, M13 and Hercules. Got it. What's next?
Next is the Hyades. This is an open cluster, and it's one of the closest to us, only about 150 light years away. Much closer.
Oh, practically next door.
Relatively speaking, yeah. It's visible as a distinct sideways V shape of stars. That V forms the face of Taurus, the bull, in the constellation.
I think I know that V shape. Isn't the bright star Aldebaran part of it?
It looks like it is. Aldebaran, that bright reddish star, sits right in the V, but it's actually much closer to us than the Hyades cluster itself. It's just a line-of-sight coincidence. The actual Hyades stars form the V around it.
Ah, tricky. Okay, Hyades and Taurus. And the third one?
The third is probably the most famous open cluster of all. The Pleiades, M45. Also known as the Seven Sisters.
Oh, everyone knows the Pleiades.
Exactly. It's unmistakable. It actually contains over 1,000 stars, mostly young, hot, white-blue ones. But it's dominated by its 7 brightest stars, which form a tiny, shimmering dipper shape.
And where do we find the Pleiades now?
In the early morning sky, look towards the east before dawn. You'll find them roughly 10 degrees or so above the Hyades cluster in Taurus. They're really stunning, even with just the naked eye, like a little patch of diamond dust.
Fantastic. M13, the Hyades, and the Pleiades. Plenty to look for. Wow, what an incredible journey we've taken today, really. From deep insights into ancient stellar collisions and how the very first molecules formed, all the way to cutting-edge AI that might help future astronauts, plus practical tips for seeing auroras and star clusters literally tonight. We really hope this deep dive has given you a wealth of knowledge, stuff you can actually digest and think about.
Absolutely. And thinking about it, all the hidden, violent pasts of stars we thought were ordinary, the unexpected chemistry that shaped the early cosmos, the AI companions for future explorers, it really makes you wonder, doesn't it? How do these discoveries keep reshaping our picture of the universe, its past, its present, and where it's all heading? And what mysteries are waiting just around the corner for the next generation to uncover?